Hey everyone, and welcome. Have you ever wondered what's really going on inside your computer when you, say, click on an icon? How does it just instantly pull up a program or a file? Well, today we are cracking the code on one of the most critical parts of your machine. It's memory. So let's just dive right in. So at its most basic level, computer memory is just an electronic space for things that need to be accessed right now. A really good way to think about it is like your own brain. It's not just for long-term storage, it's for holding all the information your computer is actively thinking about. And without it, your computer would basically be a paperweight. It just couldn't function. So here's the game plan for this explainer. We're going to follow the journey of a piece of data. We'll start with the computer's brain, that's the CPU, and why it has this constant need for speed. Then we'll unpack the really clever three-tiered system it uses. We'll look at the difference between its workspace and its library. And finally, we'll check out the super exclusive VIP lane known as cache. Okay, so let's start with the big problem that needs solving. Your computer's processor, the CPU, is just unbelievably fast. But, a fast brain is pretty useless if it can't get the information it needs just as quickly. And that is memory's #1 job, feeding that CPU at lightning speed. You see, the CPU is on this non-stop treadmill. It's constantly in a loop. Fetch an instruction, decode what that instruction means, and then execute it. To do that, it needs a direct, high-speed line to its memory. That communication happens on something called the system bus, which you can kind of picture as a multi-lane superhighway for information. And this highway, it's incredibly well organized. The CPU doesn't just, shout into the void hoping for the right data. No, it follows this really precise three-step process. First, it sends out a specific location. Think of it like a street address. Then it sends a command on a different line saying, hey, I want to read what's there, or I'm going to write something new. And finally, the actual data zips back and forth on its own dedicated lane. And we're not talking about a leisurely drive here. This entire three-step dance happens billions of times, every single second. It's the absolute foundation of everything your computer does. But it also creates this massive challenge, right? How do you possibly feed that incredible speed without making computers cost a fortune? Well, the answer is this really elegant compromise, a tiered system of memory. Instead of trying to find one perfect type of memory, which doesn't exist, computers use a whole hierarchy of different types, and each one has its own strengths, all working together to create a balanced, efficient system. And it all comes down to a really fundamental trade-off. As you go up this memory pyramid, things get way, way faster, but they also get way more expensive and a lot smaller. You just can't have it all in one package. So computers use a mix, the fastest, most expensive stuff for immediate tasks, and the slower, cheaper stuff for long-term storage. All right, let's zoom in on the two main tiers you're probably most familiar with. The best way to think about them is as your computer's temporary workspace versus its permanent library. So primary memory, or main memory, that's the active workspace. When you open your web browser or a document, or you fire up a game, it all gets loaded into this space so the CPU can work with it directly. This is where all the action is happening. Now, inside this workspace, there are two main players, RAM and ROM. Think of RAM as your work desk. It's what's called volatile, which is just a fancy way of saying when you turn the power off, everything on the desk gets wiped clean. ROM, on the other hand, is non-volatile. It's like the printed instruction manual for your computer. It holds the permanent, core instructions it needs just to start up. But what's really fascinating is that even ROM, this supposedly read-only memory, has a pretty cool history. It wasn't always as flexible as it is today. Early on, it was truly permanent, like the instructions were physically burned into the chip at the factory. And you can actually see that evolution right here. We went from that permanent masked ROM to something called PROM, which a user could program exactly once. Then came EEPROM, which, get this, you had to erase with a UV light. Not exactly user-friendly. And that all led us to the modern EEPROM we have now, which can be reprogrammed with electricity. That was a huge deal. It's what lets us do all the easy firmware updates we take for granted today. Okay, so if primary memory is the workspace and secondary memory is the library, this is your hard drive or your solid-state drive. It's where your operating system, all your apps, and all your files are stored for the long haul, just waiting to be checked out and moved to the workspace. So its role is really defined by a few key things. It's non-volatile, so your data is totally safe when the power's off. It's way cheaper per gigabyte than RAM, which is why we can have these massive storage capacities. But here's the catch. It is so much slower. And that's exactly why we don't run programs directly from the library. We have to bring them into that fast workspace first. And now we get to the very top of the pyramid, the final piece of this whole speed puzzle. This is the memory that's like an exclusive, high-speed VIP lane built just for the CPU. But hold on a second. We just established that RAM is our fast workspace, right? So why on earth would the CPU need something that's even faster than that? I mean, isn't RAM fast enough? Well, the answer is no. The CPU is so unbelievably fast that even with quick RAM, it can still end up waiting around. Cache memory solves this problem. It's a tiny, ridiculously fast buffer that sits right next to the CPU. Its whole job is to guess what the CPU is going to need next and have it ready to go, so there is literally zero waiting time. And when I say fast, I mean the speed difference is just staggering. Look, if getting data from your secondary memory is like walking to the library, and getting it from RAM is like taking a car, then getting it from the cache, that's like teleporting. The difference is just that huge. But of course, you know the drill by now. This incredible speed comes with that same old trade-off. The advantage is pure, unadulterated speed. But the disadvantages are a big deal: cost and size. Cache memory is incredibly expensive to make, and that's why you only have a few megabytes of it compared to gigabytes of RAM or even terabytes of storage. Okay, so let's tie this all together and see why this whole complex tiered system is so important for what you do on your computer every single day. Just think about launching an application. The moment you double-click that icon, the program's files are moved from the slow library on your hard drive into the fast workspace of your RAM. Then, the most critical, most frequently used bits of that program get whisked into the ultra-fast VIP lane of the cache, ready for the CPU to access instantly. So when you step back and look at it, this whole system is just a brilliant compromise. It's a balancing act. It gives the CPU the insane performance it needs with cache, it provides a big, responsive workspace with RAM, and it gives us huge, affordable, long-term storage with our drives. All those pieces working together, that's what makes modern computing possible. And that leaves us with a big question for the future. As our data just keeps growing and our demand for speed gets higher and higher, how is this elegant memory hierarchy going to have to evolve to keep up? It's a massive challenge for the next generation of computing. Thanks for joining me for this explainer.